Okay, so this is a really great question about capacity, and but it has batching involved, and it has multiple stages of batching. So there's a couple of really important things as we read through this. So first off, we operate on a 40-hour work week. Okay, there are 8 different versions of dolls, and they don't really differentiate further between those eight different dolls as you go through it, but they currently sell an average of 4,000 dolls spread equally um, among the 8 versions per week. And so this is our demand. So that might be important later. And so we just want to make note of that. Changing over between the versions requires setup time at the molding and painting stations due to the different colors of plastic pellets and blah, blah, blah. The table lists the setup times for a batch and the processing times for each unit at each step. We have unlimited space for the buffer between the steps, okay? And as company policy, each step uses the same batch size. So there is only one batch size for this problem. So assume that the setups need to be completed first, okay? So that's important because again, if we're drawing inventory graphs and things like that, sometimes we can assume that like we're starting with production, but no, we're saying, hey, setup needs to be completed first. A setup can only start once the batch has arrived at the resources. So in a typical problem, typically what we see is that while the other, we might do setup for, the first stage, while we're working and actually producing that first stage, we can actually be setting up for the second stage so that we're ready to go. We can stack those setups. You can't do that in this problem. It just makes it a little bit simpler for some of the calculations that you have to do. And then all flow units of a batch need to be processed at a resource before any of the units can be moved to the next resource. Okay. So it gives us the setup time, right? It's telling us that the molding and the painting are batching processes. Okay. So their capacity actually depends on the batch size. But the dressing, which has no setup time, it's a steady, constant resource. It's not batching. And what this triggers to us immediately is that at some point, I'm probably going to have to set up the molding and painting to match what's happening at the dressing, okay? Because typically we're always scaling our batching processes up or down to match the non-batching process. So it asks us here for A, what's the process capacity in units per hour of a batch size of 500 dolls? Okay, so it gives us that batch size of 500. And it asks us for the process capacity. So to find the process capacity, we have to find the capacity of each one of these events because they're going to go from molding into a buffer, then into painting, into a buffer, and then into dressing. There are going to be 3 different things there. So for molding or step 1, we're going to use the capacity formula for a batching process, right? So for step 1, now that capacity formula, which when we're using our batching formula is going to be our batch size over our setup time plus the batch size times process time. Remember, guys, all this really is units produced, right? Whatever our batch size is, over that total time to produce them. So for stage 1, yes, they're making 500 at a time. It is taking them 15 minutes for that setup time, and then a quarter of a minute for each of those 500 units there. Okay, so it's taking them, if we calculate out that denominator, 140 minutes to make 500 dolls, right? This is dolls. So our capacity there becomes Well, I can't do that in my head. I love how I could do one of them. 3 point, we might as well leave that as a fraction. 25 over 7 joules per minute. And remember, if it's per something and I want to turn it into per hour, I multiply by 60. This might give us a nicer answer. Pretty close. So we get 214.286 joules per hour. These are whole unit joules, so we can probably work with that 214. Okay. And we do the same thing for step 2. So step 1 at a capacity or a batch size of 500 is able to, when you average all this out, spit out 214 joules per hour. Step 2 there, okay, that capacity, following that same setup, same formula for producing 500, it takes us 30 minutes of setup plus 0.15 for each of those 500. Okay, so what is that? It's 105 minutes to actually make that. It's going to be a messy one. 500 divided by 105 gives me 4.76. And I'm going to multiply that by 60 just to keep everything simple. And I get 285.7. And so we can work with that as just the round number, joules per hour. Okay. And for step 3, oops, for capacity, now for this one, you can think about it as like still having to do the whole batch. Like, you know, I'm going to do 500. How long does it take me to produce 500? Right? There's 0 setup time plus it's 0.3 for each of those 500. This is the same as that 1 over the time it takes to produce 1 unit there. Okay, so 1 divided by 0.3 tells us that we could do 3.33 per minute. And then if I multiply that by 60, this means that we have 200 per hour. So for A here, the actual answer for A is that the process capacity is going to actually be 200 per hour because that's our bottleneck, right? Stage, not 30, stage 3 is the bottleneck. Now, what this does mean is that we could probably adjust step 1 and step 2 because they're batching processes to spit out that 200 per hour. Question B asks us, what's the time it takes for the first batch of $500 to go through an empty process? This is where this assumption 2 is really important. A setup can only start once the batch has arrived at the resources. Otherwise, we wouldn't incur this 30 minutes of setup time for painting because we could do that while molding is going. But because we do have that assumption, we have to. So we're going to start with that setup time for molding. So 15 minutes, right? Then we actually have to do all of the molding. So that takes 0.25 minutes for each of those 500 units. Once they're done, they go to painting. And now that they've arrived at painting, they're allowed to do the setup for painting. And again, if that assumption wasn't there, that 30 minutes wouldn't be there because we could have done that 30 minutes of setup while we were going through the first stage there, plus that 0.15 for each of those 500. And then for the dressing, right, there's no setup. And it's 0.3 for each of those 500 there. And so this equals 395 minutes. Okay. Those ones are usually okay. Where people start to be like, what is happening in this problem is what batch size would minimize inventory without decreasing the process capacity? And what I want to say here is I'm going to answer it a little bit differently than I think the answer is in your textbook because based off of the questions that people have asked me, just so that we can, I think it's a little bit easier to see what I'm saying. Okay, so for C, what batch size would minimize inventory without decreasing process capacity? What we want to recognize for C is that our process capacity is that 200 per hour. And so what we want to do is for stage 1 and stage 2, use that batch sizing formula to figure out what batch size will give us a flow rate, right? An output, a capacity, however you want to describe it, of 200 per hour, okay? So our goal here is to find the batch size for each that generates 200 units per hour, okay? So for step 1, our setup time hasn't changed, right? It's 15 minutes. Our process time is at 0.25. But our desired flow rate, aka the capacity, is 200 per hour. So my batch size, which is my flow rate times setup over 1 minus that flow rate times my process time, or unit time, depending on kind of what version of the formula you're looking at, but it's all the same thing. We want to calculate this. The only thing here is that my setup time, my process time are both in minutes. And so my flow rate, which is 200 per hour, I'm going to divide that by 60. And I'm going to go back to that 3.33 repeating so that it's per minute. Okay, and I will actually put that in as 10 over 3 just to not mess up. Like if you can carry through that fraction, do that. So we need to produce 10 over 3. Our setup time is 15. 1 minus that 10 over 3 times 0.25. Okay, and I get a batch size of 300 here. Okay, for step 2, we're going to do the same thing, right? Our setup time is 30 minutes. Our process time is 0.15 minutes. And our goal here is still to have that flow rate of 200 per hour or 10 over 3 per minute. And so when I calculate my batch size here, okay, same thing. So my flow rate times my setup time over 1 minus my flow rate times my process time. So what do I get here? So I get 200. Now, this is the thing, is that we can actually only have one batch size in this problem. And what happens is that if I were to use a batch size of 200 in step 1, right? Because the answer is either 200 or 300. But which one is it? Okay. And the truth is that we have to just use the larger of the two batch sizes, okay? Because if I take this batch size of 200 and I put that into step 1, I'm not going to get 200 per hour coming out, okay? If I take my batch size of 300 and I put it into step 2, I'm going to increase that flow rate or that capacity. So what we have to understand, right, is that the larger the batch size, the greater the flow rate. So we can always have a bigger batch size. Our goal is to minimize inventory. I could just pick a batch size of 1,000, or like we just did above, 500. And for both step 1 and step 2, they were able to exceed that $200 per hour. But the problem that happened there is that we just have a buildup of inventory between the buffers. And our goal here was to minimize inventory. So we're trying to bring these in line as much as possible. So in order to do that, we have to pick the greater of the two options. If this problem allowed us to use different batch sizes for each process, we would actually use the 2 different batch sizes. Because this problem only allows one batch size through the whole process, we have to pick between that 200 and 300, and we're going to pick the larger of the 2. Because these are, we can think about them as the minimum batch size to produce 200 per hour. And because they both have to be the same, we have to meet both of those minimums. For this part C, we are going to use a batch size of 300, okay, for the system. We will only produce 200 per hour, okay? And in this situation, if we're producing 200 per hour, stage 1 is a bottleneck because we used its batch size. It's going to actually just be producing exactly 200 per hour. Stage 2 will have extra capacity. It will actually be producing at a rate greater than 200 per hour. And stage 3 is still a bottleneck at 200 per hour. Okay. Now I know in the textbook, I think they actually go through and they find the break-even point between stage 1 and stage 2. I didn't ask you to find the break-even point, so I would honestly just solve for both and then pick the larger of the 2 numbers, knowing that really what you've done is created the minimum batch size required there. Now we get to question part D, and part D asks us, which batch size would minimize inventory without decreasing the current flow rate? And this is going to be the exact same as C, except we're not talking about process capacity, we're talking about flow rate. And one of the things we want to recognize here, okay, is flow rate is going to be the minimum between our bottleneck and demand. So in part C, when it just asked the process capacity, we didn't have to consider demand. We were just using the bottleneck. But for part D, right, where it actually asks us about our flow rate, the current flow rate, when we're looking at the whole problem, that is the minimum between our bottleneck, right, which is our process capacity, and demand. So in this situation, they'd given us demand information. They told us that the demand was $4,000 per week. And they also said that they work a 40-hour work week. So our demand here, right, going to be 100 per hour. So if we produced under C, which I would recommend anyways, we could just work for half of the time, right? Produce 200 per hour, stop after 20 hours, you've made your $4,000. But that's not what this question asks us. It asks us, well, what batch size do we need to use in order to deal with the current flow rate? And so that's just doing the exact same process that we did, but now setting it for 100 per hour, not 200 per hour. And so again, because everything else I had was in minutes, I'm going to take that 100 per hour and just divide it by 60 to get the fact that this is 5 out of 3 per minute that I need to be producing. For step 1, that batch size, right? I'm going to take that flow rate that I want, that 5/3, times my setup time, 15, 1 minus flow rate times that time per unit. Give me so here I get 42.85, so about 43 per batch. In step 2, that batch size, 5 out of 3. Our setup time there was 30 minutes. Oops. 1 minus that 5/3 times our time per unit, which was 0.15. I cannot put things in my calculator this morning. What do we have? We have 50 on the top. I really can't put things into my calculator. Welcome to fun. Okay, and then here we get 66.66, so 67. And again, in order to meet a flow rate, or in order to meet the flow rate for the whole system, these are the minimum required batch size. And because we can only have one batch size for the whole process, we just have to pick the larger of the two. So in this question, we would need a batch size of 67, okay? Because you do need to pick that minimum of, like, the bigger of the two, because these are minimums. You have to meet both minimums. So by picking 67, we met the minimum of 43 and the minimum of 67. Same thing up here. By picking 300, we met the minimum of 300 and the minimum of 200. So hopefully that is helpful instead of finding the break-even point and then going from there. Good luck.